Hello everyone, welcome back to 3 Deviations. In today's video we are going to finish Unit 9. So we're going to finish discussing Taylor series and series as a whole. So this is really the capstone of everything we've done. So we've discussed how to build Taylor series, we've discussed the Lagrange remainder, and we've discussed how to manipulate the Taylor series. So what is left to do is to discuss how to apply the Taylor series. So the way I would view the Taylor series is basically as a generalization of linear approximation. Back in Calculus 1, what we learned is that we can have a graph and we can find its tangent line. We can use this tangent line to approximate the value of a function. Like we could approximate its value right there using the linear approximation. In the linear approximation, the formula for the linear approximation, L of x was equal to f of x minus, the linear approximation at f equals a, L of x at x equals a is equal to f of a plus f prime of a times x minus a. Now what does this look like? Well, this is exactly the same. This is equivalent to the first order Taylor polynomial of the function. So we've determined that the linear approximation, the tangent line, at a point is the first order Taylor approximation. That should make a lot of sense. We're approaching what I would call like a classical limit. We're approaching the Taylor series is a generalization, but it gets to the limit at the right place. So, well, what do we do to generalize this? Well, what we do is we add terms. So we found a linear approximation. We can also find a quadratic approximation. We could find a cubic approximation and a quartic approximation, a quintic, and we can keep adding equations. And these add a lot more consistency and a lot less error to our graph. As you can see here, this little guy here between the function and the linear approximation is called the error. So we can play around with the error. We can say, how big do we want the error to be before we consider something not to be a valid approximation? So that's what we're going to talk about in today's video. We're going to be playing around mostly with the sine function today. So let's do an example. I would like us to find the error of the fifth order Taylor series for x for the sine function on the interval between negative 0.3 and 0.3. Okay, so what we need to do is we need to remember the Lagrange formula. Lagrange formula says that the remainder of the nth polynomial of x is equal to the maximum of the nth plus 1 derivative of x on that interval times x minus a to the nth plus 1 power over n plus 1 factorial. So this is basically, less than. This is essentially, or greater than, I can't remember here. But essentially we are equating it, the error, the magnitude of the error, to the next order term in our Taylor polynomial. Now for sine, this is a little bit tricky, because for the sine function, the problem is that our alternating series determines that our even numbered terms cancel out. So we need to go to the seventh order to find the next one. So the remainder for the fifth is going to be equal to the maximum of the nth plus 1 times x minus a to the n plus 1 over n plus 1. Of course, a is 0. We're centering our polynomial at 0. And also, n plus 1 is going to need to go to 7 because 6 would go to 0. Anyways, from here, we can get a nice formula here. We take the next term of the series, of the Taylor series, which is x to the 7th over 7 factorial for the sine of x. And of course, we're multiplying this by the maximum of that derivative, and the maximum of that derivative is going to be 1 because it's a trigonometric function, so it has a maximum at 1. And we can do this out, and we can plug in our x, so we get 0.3 to the 7th over 5040, which is about 4.3 times 10 to the negative 8th. So that's pretty cool. What we've determined is that if we use the Quintic approximation for sine of x, So if we have sine of x here, this is what I think got pi here, we've got negative pi here. What we've determined is that on the interval between about here and here, our error is extremely negligible, 4.3 times 10 to the negative 8th. So you can use our Quintic approximation, which I think looks something like this, to approximate our sine function with relatively low error. So that is how we determine the error, but now we should determine, we should go the other way around. So for what interval is this fifth order Taylor polynomial for sine x valid within 0.00005? Okay, so now we're going the other way. So now we need to set the error equal to 0.0005. We use a similar formulation. We get x to the 7th magnitude over 7 factorial is less than or equal to 0.00005. Okay, so now all that's left is some arithmetic, and then we can find x. So we find that the value here is 0.822. So that's also pretty good. But pretty much between -1 and 1, we can use this Taylor series to a very accurate amount. So that's pretty interesting. So that's really what we've done with these Taylor series. So I would like to also kind of ruminate on other places where this is used. It's not used as rigorously. It's mostly used to make our lives easier in physics. But essentially, in many physics textbooks, you'll get formalisms where they'll give you functions. You'll get logs. You'll get exponentials. You'll get trig. And the idea is, instead of using these, you are going to put them in terms of series, usually maybe a 5th order or 3rd order polynomial of a Taylor series. The reason you do that is because these guys are usually super ugly, and you are going to want to differentiate them, or you're going to want to integrate them. And it's going to be a lot easier when you have these polynomials as opposed to your elementary functions. So this is really what we've done in Unit 9. It's been a long time, but I think it's been a very important unit to cover. We have covered the infinite is basically what we have done in Unit 9. We started off with series. We moved on to all of the tests for series and the ways that we can estimate the series. Then we talked about the power series and how we can perform calculus with them. Then we looked at Taylor series, how we can make them. The Maclaurin series. We looked at Lagrange error, and we looked at how to differentiate and integrate those series as well. And what we've arrived at is a way to rewrite any type of function that we want and make it more usable for us when we want to perform calculus on it. I just think that's a really amazing thing that we've learned how to do. All right. Anyways, in the next video, we are going to be moving on to Unit 10. So we will start by discussing parametric equations algebraically. Then we will look at parametric equations with calculus. Then we will look at polar curves algebraically. Then we will look at polar derivatives, polar areas, polar arc lengths, and then we are done. Thank you for watching, and we will see you next time. Bye.